In mathematics, general topology is the branch of topology that deals with the basic set-theoretic definitions and constructions used in topology. It is the foundation of most other branches of topology, including differential topology, geometric topology, and algebraic topology. Another name for general topology is point set topology. The fundamental concepts in point set topology are continuity, compactness, and connectedness. Continuous functions, intuitively, take nearby points to nearby points. Compact sets are those that can be covered by finitely many sets of arbitrarily small size. Connected sets are sets that cannot be divided into two pieces that are far apart. The words nearby, arbitrarily small, and far apart can all be made precise by using open sets. If we change the definition of open set, we change what continuous functions, compact sets, and connected sets are. Each choice of definition for open set is called a topology. A set with a topology is called a topological space. Metric spaces are an important class of topological spaces where distances can be assigned a number called a metric. Having a metric simplifies many proofs, and many of the most common topological spaces are metric spaces. History. General topology grew out of a number of areas, most importantly the following: the detailed study of subsets of the real line, the introduction of the manifold concept, the study of metric spaces, especially normed linear spaces, in the early days of functional analysis. General topology assumed its present form around 1940. It captures, one might say, almost everything in the intuition of continuity, in a technically adequate form that can be applied in any area of mathematics. A topology on a set. Let X be a set and let tau be a family of subsets of X. Then tau is called a topology on X if both the empty set and X are elements of tau. Any union of elements of tau is an element of tau. Any intersection of finitely many elements of tau is an element of tau. If tau is a topology on X, then the pair is called a topological space. The notation X tau may be used to denote a set X endowed with the particular topology tau. The members of tau are called open sets in X. A subset of X is said to be closed if its complement is in tau. A subset of X may be open, closed, both, or neither. The empty set and X itself are always both closed and open. Basis for a topology A. Base B for a topological space X with topology T is a collection of open sets in T such that every open set in T can be written as a union of elements of B. We say that the base generates the topology T. Bases are useful because many properties of topologies can be reduced to statements about a base that generates that topology, and because many topologies are most easily defined in terms of a base that generates them. Subspace and quotient. Every subset of a topological space can be given the subspace topology in which the open sets are the intersections of the open sets of the larger space with the subset. For any indexed family of topological spaces, the product can be given the product topology, which is generated by the inverse images of open sets of the factors under the projection mappings. For example, in finite products, a basis for the product topology consists of all products of open sets. For infinite products, there is the additional requirement that in a basic open set, all but finitely many of its projections are the entire space. A quotient space is defined as follows. If X is a topological space and Y is a set, and if f x y is a surjective function, then the quotient topology on Y is the collection of subsets of Y that have open inverse images under F. In other words, the quotient topology is the finest topology on Y for which F is continuous. A common example of a quotient topology is when an equivalence relation is defined on the topological space X. The map F is then the natural projection onto the set of equivalence classes. Examples of topological spaces. A given set may have many different topologies. If a set is given a different topology, it is viewed as a different topological space. Any set can be given the discrete topology in which every subset is open. The only convergent sequences or nets in this topology are those that are eventually constant. Also, any set can be given the trivial topology, in which only the empty set and the whole space are open. Every sequence and net in this topology converges to every point of the space. This example shows that in general topological spaces, limits of sequences need not be unique. However, often topological spaces must be Hausdorff spaces where limit points are unique. There are many ways to define a topology on R, the set of real numbers. The standard topology on R is generated by the open intervals. The set of all open intervals forms a base or basis for the topology, meaning that every open set is a union of some collection of sets from the base. In particular, this means that a set is open if there exists an open interval of non-zero radius about every point in the set. More generally, the Euclidean spaces Rn can be given a topology. In the usual topology on Rn, the basic open sets are the open balls. Similarly, C, the set of complex numbers, and Cn have a standard topology in which the basic open sets are open balls. Every metric space can be given a metric topology, in which the basic open sets are open balls defined by the metric. This is the standard topology on any normed vector space. On a finite-dimensional vector space, this topology is the same for all norms. Many sets of linear operators in functional analysis are endowed with topologies that are defined by specifying when a particular sequence of functions converges to the zero function. Any local field has a topology native to it, and this can be extended to vector spaces over that field. Every manifold has a natural topology since it is locally Euclidean. Similarly, every simplex and every simplicial complex inherits a natural topology from Rn. The Zariski topology is defined algebraically on the spectrum of a ring or an algebraic variety. On Rn or Cn, the closed sets of the Zariski topology are the solution sets of systems of polynomial equations. A linear graph has a natural topology that generalizes many of the geometric aspects of graphs with vertices and edges. The Sierpinski space is the simplest non-discrete topological space. It has important relations to the theory of computation and semantics. There exist numerous topologies on any given finite set. Such spaces are called finite topological spaces. Finite spaces are sometimes used to provide examples or counterexamples to conjectures about topological spaces in general. Any set can be given the cofinite topology in which the open sets are the empty set and the sets whose complement is finite. This is the smallest T1 topology on any infinite set. Any set can be given the co-countable topology, in which a set is defined as open if it is either empty or its complement is countable. When the set is uncountable, this topology serves as a counterexample in many situations. The real line can also be given the lower limit topology. Here, the basic open sets are the half-open intervals a, b. This topology on R is strictly finer than the Euclidean topology defined above. A sequence converges to a point in this topology if and only if it converges from above in the Euclidean topology. This example shows that a set may have many distinct topologies defined on it. If gamma is an ordinal number, then the set gamma equals 0. Gamma may be endowed with the order topology generated by the intervals 0, b, and where her A and b are elements of gamma. Continuous functions. Continuity is expressed in terms of neighborhoods. F is continuous at some point xx if and only if for any neighborhood v of f, there is a neighborhood u of x such that fv. Intuitively, continuity means no matter how small v becomes, there is always a u containing x that maps inside v and whose image under f contains f. This is equivalent to the condition that the pre-images of the open sets in Y are open in X. In metric spaces, this definition is equivalent to the epsilon delta definition that is often used in analysis. An extreme example: if a set X is given the discrete topology, all functions to any topological space T are continuous. On the other hand, if X is equipped with the indiscrete topology and the space T set is at least T0, then the only continuous functions are the constant functions. Conversely, any function whose range is indiscrete is continuous. Alternative definitions: several equivalent definitions for a topological structure exist, and thus there are several equivalent ways to define a continuous function. Neighborhood definition: definitions based on pre-images are often difficult to use directly. The following criterion expresses continuity in terms of neighborhoods. F is continuous at some point XX if and only if for any neighborhood V of F, there is a neighborhood U of X such that Fv. Intuitively, continuity means no matter how small V becomes, there is always a U containing X that maps inside V. If X and Y are metric spaces, it is equivalent to consider the neighborhood system of open balls centered at X and F instead of all neighborhoods. This gives back the above delta epsilon definition of continuity in the context of metric spaces. However, in general topological spaces, there is no notion of nearness or distance. Note, however, that if the target space is Hausdorff, it is still true that F is continuous at A if and only if the limit of F is X approaches A is F. At an isolated point, every function is continuous. Sequences and nets: in several contexts, the topology of a space is conveniently specified in terms of limit points. In many instances, this is accomplished by specifying when a point is the limit of a sequence, but for some spaces that are too large in some sense, one specifies also when a point is the limit of more general sets of points indexed by a directed set, known as nets. A function is continuous only if it takes limits of sequences to limits of sequences. In the former case, preservation of limits is also sufficient. In the latter, a function may preserve all limits of sequences yet still fail to be continuous, and preservation of nets is a necessary and sufficient condition. In detail, a function f x, y is sequentially continuous if whenever a sequence in X converges to a limit X, the sequence converges to F. Thus sequentially continuous functions preserve sequential limits. Every continuous function is sequentially continuous. If X is a first countable space and countable choice holds, then the converse also holds. Any function preserving sequential limits is continuous. In particular, if X is a metric space, sequential continuity and continuity are equivalent. For non-first countable spaces, sequential continuity might be strictly weaker than continuity. This motivates the consideration of nets instead of sequences in general topological spaces. Continuous functions preserve limits of nets, and in fact this property characterizes continuous functions. Closure operator definition: instead of specifying the open subsets of a topological space, the topology can also be determined by a closure operator, which assigns to any subset AX its closure, or an interior operator, which assigns to any subset A of X its interior. In these terms, a function between topological spaces is continuous in the sense above if and only if for all subsets A of X, that is to say, given any element X of X that is in the closure of any subset A, F belongs to the closure of F. This is equivalent to the requirement that for all subsets A of X, moreover, is continuous if and only if for any subset A of X. Properties: if F, X, Y and G, Y, Z are continuous, then so is the composition G, F, X, Z. If F, X, Y is continuous and X is compact, then F is compact. X is connected, then F is connected. X is path connected, then F is path connected. X is Lindelof, then F is Lindelof. X is separable, then F is separable. The possible topologies on a fixed set X are partially ordered. A topology tau1 is said to be coarser than another topology tau2 if every open subset with respect to tau1 is also open with respect to tau2. Then, the identity map IDX is continuous if and only if tau1 tau2. More generally, a continuous function stays continuous if the topology tau-y is replaced by a coarser topology or tau-x is replaced by a finer topology. Homeomorphisms symmetric to the concept of a continuous map is an open map, for which images of open sets are open. In fact, if an open map F has an inverse function, that inverse is continuous, and if a continuous map G has an inverse, that inverse is open. Given a bijective function f between two topological spaces, the inverse function f-1 need not be continuous. A bijective continuous function with continuous inverse function is called a homeomorphism. If a continuous bijection has as its domain a compact space and its codomain is Hausdorff, then it is a homeomorphism. Defining topologies via continuous functions given a function where X is a topological space and S is a set. The final topology on S is defined by letting the open sets of S be those subsets A of S for which F-1 is open in X. If S has an existing topology, F is continuous with respect to this topology if and only if the existing topology is coarser than the final topology on S. Thus the final topology can be characterized as the finest topology on S that makes F continuous. If F is surjective, this topology is canonically identified with the quotient topology under the equivalence relation defined by F. Dually, for a function f from a set S to a topological space, the initial topology on S has as open subsets A of S those subsets for which F is open in X. If S has an existing topology, F is continuous with respect to this topology if and only if the existing topology is finer than the initial topology on S. Thus the initial topology can be characterized as the coarsest topology on S that makes F continuous. If F is injective, this topology is canonically identified with the subspace topology of S, viewed as a subset of X. More generally, given a set S, specifying the set of continuous functions into all topological spaces X defines a topology. Dually, a similar idea can be applied to maps. This is an instance of a universal property. Compact sets. Formally, a topological space X is called compact if each of its open covers has a finite subcover. Otherwise it is called non-compact. Explicitly, this means that for every arbitrary collection of open subsets of X such that there is a finite subset J of A such that some branches of mathematics, such as algebraic geometry, typically influenced by the French school of Bourbaki, use the term quasi-compact for the general notion, and reserve the term compact for topological spaces that are both Hausdorff and quasi-compact. A compact set is sometimes referred to as a compactum, plural compactor. Every closed interval in R of finite length is compact. More is true. In Rn, a set is compact if and only if it is closed and bounded. Every continuous image of a compact space is compact. A compact subset of a Hausdorff space is closed. Every continuous bijection from a compact space to a Hausdorff space is necessarily a homeomorphism. Every sequence of points in a compact metric space has a convergent subsequence. Every compact finite-dimensional manifold can be embedded in some Euclidean space Rn. Connected sets. A topological space X is said to be disconnected if it is the union of two disjoint non-empty open sets. Otherwise, X is said to be connected. A subset of a topological space is said to be connected if it is connected under its subspace topology. Some authors exclude the empty set as a connected space, but this article does not follow that practice. For a topological space X, the following conditions are equivalent. X is connected. X cannot be divided into two disjoint non-empty closed sets. The only subsets of X that are both open and closed are X and the empty set. The only subsets of X with empty boundary are X and the empty set. X cannot be written as the union of two non-empty separated sets. the only continuous functions from x to 0, 1, the two-point space endowed with the discrete topology, are constant. Every interval in R is connected. The continuous image of a connected space is connected. Connected components. The maximal connected subsets of a non-empty topological space are called the connected components of the space. The components of any topological space X form a partition of X. They are disjoint, non-empty, and their union is the whole space. Every component is a closed subset of the original space. It follows that, in the case where their number is finite, each component is also an open subset. However, if their number is infinite, this might not be the case. For instance, the connected components of the set of the rational numbers are the one-point sets, which are not open. Let be the connected component of X in a topological space X, and be the intersection of all open closed sets containing X. Then where the equality holds if X is compact Hausdorff or locally connected. Disconnected space is a space in which all components are one-point sets is called totally disconnected. Related to this property, a space X is called totally separated if, for any two distinct elements x and y of X, there exist disjoint open neighborhoods U of X and V of Y such that X is the union of U and V. Clearly any totally separated space is totally disconnected, but the converse does not hold. For example, take two copies of the rational numbers q, and identify them at every point except 0. The resulting space, with the quotient topology, is totally disconnected. However, by considering the two copies of 0, one sees that the space is not totally separated. In fact, it is not even Hausdorff, and the condition of being totally separated is strictly stronger than the condition of being Hausdorff. Path-connected sets. A path from a point x to a point y in a topological space X is a continuous function f from the unit interval 0, 1 to x with f equals x and f equals y. A path component of X is an equivalence class of X under the equivalence relation, which makes X equivalent to Y if there is a path from X to Y. The space X is said to be path-connected if there is at most one path component, i.e., if there is a path joining any 2 points in X. Again, many authors exclude the empty space. Every path-connected space is connected. The converse is not always true. Examples of connected spaces that are not path-connected include the extended long line L** and the topologist's sine curve. However, subsets of the real line R are connected if and only if they are path-connected. These subsets are the intervals of R. Also, open subsets of Rn or Cn are connected if and only if they are path-connected. Additionally, connectedness and path-connectedness are the same for finite topological spaces.